SANDHAN, all Gujarat integrated classroom.
સેટેલાઇટ ના માધ્યમથી જોડતી કડી એટલે સંધાન.
Good afternoon to all the viewers. Today I am here to discuss a topic of physics related to bridges, AC and DC bridges. First of all, what's new about bridges? We have been already measuring voltage and current using different kind of meters, but the difference between that is to be discussed. First of all, no electrical metering discussion could be called complete without bridge circuit. These circuits make use of null balance meter to compare two voltages, just like laboratory balance scales compares the weights and indicates their equal. A bridge. A bridge is a circuit in its simplest form containing four network arms. Each of them is containing either resistors or different reactants and forming a closed circuit. Further, the circuit is excited with a source of current or voltage and the current detector is connected to the other two junctions. Here you can see that R1, R2, R3 and R4 four resistors are connected and connected with a null detector. We are applying here DC excitation, while in the adjacent circuit we are having Z1, Z2, Z3 and Z4 four reactances connected along with a null detector excited with AC source. A bridge. A bridge circuit are extensively used for measuring component values such as R, L and C. A bridge circuit compares the value of an unknown component with that of the accurately known component, a standard value. We are using a standardized resistor so that the resistance is highly accurate and that is being compared, so measurement is also comparatively very high accurate. Bridge. Readout of a bridge is based on a null indication of balance, hence its independence of the characteristic of null detector. Here we are interested in measuring whether the galvanometer is indicating null or not, whether an AC headphone is also indicating no sound or not. That is making the measurement system independent of the type of detector. Measurement accuracy. Measurement accuracy depends on an accuracy of the bridge components. So everything that depends on the bridge components, higher the accuracy of the bridge components, higher is the measurement accuracy. Depending on the kind of excitation provided to the bridge may be classified as either DC bridge or AC bridge, and detectors are also selected accordingly. Normally a galvanometer is selected for DC bridge and a headphone for AC bridge is sufficient. For requirement of higher accuracy or higher resolution, the galvanometer may be replaced with a VTVM and the headphone may be replaced with high precision AC millivoltmeter. First of all, starting with DC bridges. DC bridges require DC excitation, and in this category we are having two bridges for the discussion. First of all, the very popular Wheatstone Bridge, 4 resistance arm measurement of 1 ohm or above. While Kelvin's bridge, which is required for a very low resistance measurement, the resistance range starts from 1 ohm reaching to a bottom level of 0.0001 ohm. The first one and the most popular one, Wheatstone Bridge, a simple 4-arm network containing a galvanometer at the center and excitation with a DC voltage. Whatever is this circuit, if I want to go for that, the balancing of the bridge is required, and that balancing conditions are mentioned in the next slide. In order to balance the bridge, the current passing through the resistor R1 and R3 should be same as that of the I2 and R2 and R4. That is making I1 is equal to I3, and in brief, voltage divided by the total of the resistors R1 and R3, while I2 is equal to I4, that is the current through the second two arms I2 and I4, that is voltage divided by total of the two resistors. This is a condition that is making null detection, that is the current passing through one of the branch is not passing through the other branch, so the galvanometer is showing null deflection or zero current. In this condition, the voltage drop across the two junctions D and B are voltage at junction D is equal to voltage of excitation multiplied by R3 upon R1 plus R3, while voltage at the junction B is equal to voltage multiplied by R4 upon R2 plus R4. So both of the branches are working as a simple potential divider, and the potential divider voltage that is available at junction D and B should be equal. At the same circuit, we are looking at the currents I1, I2, I3 and I4. In the null condition, I1 current has to be equal to I3 and I2 current has to be equal to I4 current. The same thing that we have talked in the last session, that is the voltage drop across or voltage at the junction D is equal to total excitation voltage multiplied by R3 upon R1 plus R3, while the voltage at junction B is equal to total voltage applied excitation multiplied by R4 upon R2 plus R4. Showing the balance condition, that is voltage at two junctions D and B should be equal, that is expanding the expression, that is voltage at R3 D is equal to voltage at B, that is VR3 upon R1 plus R3 is equal to V into R4 upon R2 plus R4. Reducing this expression, we can get finally the expression at the bottom, that is R4 is equal to R3 into R2 divided by R1. Now this particular expression can help you in defining or finding the value of an unknown resistor. Here the same Wheatstone bridge is connected, but R4 is replaced with an unknown resistance Rx. Now in this case, we are having the same expression written in a different way, that R4 is equal to R3 R2 upon R1. Here R4 gets replaced by Rx and the expression becomes Rx is equal to R2 R3 upon R1 in the null condition. Wheatstone bridge applications. The applications of Wheatstone bridge includes, first of all, resistance measurement of wires or different resistors, the DC resistance measurements of motor windings, transformers, solenoids, relay coils, etc. etc. Also it is used to locate cable faults for the telephone line. Basically, solenoids or a Wheatstone bridge are used for resistance measurement above the value of 1 ohm or larger. A simple example of finding a short circuit loop. Here is shown a telephone line following with a simple circuit that is utilized. We are connecting the circuit of a telephone loop with a short circuit in a Wheatstone bridge. In this condition, again we are trying to define the null condition, and in this condition the ratio of resistor arms R1 and R2 is to be found. Now this particular ratio helps in finding the location of short circuit, so that it is quite possible to go for a dedicated location or a precise location where it is possible to find a short circuit. An example is given here. The example definition: the Murray loop test is used to locate a ground fault in telephone system. The total resistance of the cables R1 plus R2 is measured to be 300 ohms. The conditions for Murray loop test conditions are defined as R3 is equal to 1000 ohms and R4 is equal to 500 ohms for nulling. Find the location of the fault in meter if the length per ohm is 36.67 meters. Now this particular idea is available, and this particular idea can help you in finding the location or the distance of short circuit. Replacing the values that is given R1 plus R3 and R4, this particular solution gives you R1 is equal to 200 ohms while R2 is equal to 100 ohms. Finding the location of short circuit, the ohms resistance multiplied by the distance per ohm, that is 100 ohms multiplied by 36.67 meters, giving you a distance of location or short circuit, that is where the short circuit has occurred, that is 36.67 meters. So this is how we can go for short circuit finding, and this is the earliest method of finding whether there is a short circuit at which particular location. In that case, this can be helpful. The Wheatstone bridge is having certain limitations also. The first limitation, it is not suitable for very low resistance measurement, because in this case the leakage resistance or the connecting lead resistors are also coming in picture, and that can affect the accuracy of measurement. The second one, very high resistance measurement. If we are going for very high resistance measurement, then we require to replace galvanometer by a VTVM. And third one, that is heating effect of resistance due to current through the arms. It is quite possible that whenever we are passing current through the resistors, it gets heated due to the current, and that can change the inherent resistance of itself. So whatever are the predefined values of resistance, that does not remain same, and in turn it can affect the measurement accuracy. Here is a same Wheatstone bridge shown with certain detailing. The R3 and Rx, two arms are connected, and we are supposed to have a very low resistance of R3 and R4. If we are having very high resistance or moderate value of resistors of R3 and Rx, then the contact resistance that has been indicated by Ry between the terminals M and N does not be that much significant. But if the values of R3 and Rx are small enough, then the value of that particular contact resistance is becoming significant, and that can affect the measurement sensitivity. In the given circuit, Ry is presenting the connecting lead resistance between the terminal resistors R3 and Rx. The galvanometer may be connected at any point P between the points M and N, and depending on the direction in which it is connected, whether it is connected to M or whether it is connected towards N, it can add up that resistance to a particular measurement value of R3 and Rx. So the same thing is dictated here, that the resistance between the points P and M, RPM between points P and N, RPN, gets added to the values of R3 and Rx respectively, and ultimately whatever we are measuring is R3 plus RPN and Rx plus RPM. If the point P is selected in such a way that the ratio of RPM to RPN, that is the ratio of resistance from the contact point towards R3 and R4, are equal to the ratio of R2 and R1, the bridge balance condition becomes as given: Rx plus RPN, that is equal to R1 by R2 multiplied by R3 plus RPM. But as we have defined, Ry is equal to RPN plus RPM, that is total contact resistance, and RPM upon RPN is equal to the ratio of R2 by R1. This gives you a solution that RPM by RPN getting replaced, and ultimately it results in a value of RPN to be defined as R2 Ry upon R2 plus R1, and RPM is defined as R1 Ry upon R1 plus R2. Substituting the values of RPM and RPN, we get finally the last expression, that is Rx is equal to R1 R3 upon R2. This is possible if we are having the condition specified on the first row, that is RPM upon RPN is equal to R2 upon R1, that is the ratio of the two arms that we have utilized is equal to, or is supposed to be equal to, the ratio of the contact lead resistors. Now this particular thing is making the base of the principle of Kelvin's double bridge. As it is not possible to define the contact resistance to be in exact ratio, we are doing something else. We are applying two more arms to the same Wheatstone bridge. So it is now having two additional pairs of arm with resistors Ra and Rb, making the same bridge expanded. Here the galvanometer is connected between the junctions defined by R1 and R2 and defined by Ra and Rb, that is between points P and between points K. Now in this condition, the voltage drop across R1 is same as the voltage drop across Rx and Ra, and also the voltage drop across R2 should be equal to the voltage drop across R3 and Rb combinedly. That is, in this case, VLK should be equal to VLMP and VAK, that is equal to VANP. Now this can be seen in the same diagram, that is VLK, that is the voltage drop across the resistor R2 should be equal to the sum of the voltage drop across R3, that is VLM, plus the voltage across RB, that is MP. So VLMP should be equal to the VLK, and in the same, that is in the lower arms, the voltage drop across R1, that is equal to VOK, should be equal to the voltage drop across arms Rx and Ra, that is VONP. Now this is making the balance conditions of the bridge, that is, if the voltage at the points defined in this diagram, that is at point K is equal to point P, then it is to be defined in this way, that is VLK is equal to R2 upon R1 plus R2 into excitation voltage. In this particular condition, the voltage is equal to current multiplied by R of the particular arm, that is R3 plus Rx plus the parallel resistance of Ra plus Rb upon Ry. So this particular resistor is appearing in this particular condition. So VLMP is getting value of I multiplied by R3 plus Ry upon Ra plus Rb plus Ry, that is parallel resistance of Ra, Rb and Ry multiplied by Rb. So this is the voltage drop across the branch, across the loop, VLMP. This particular expression can be reduced further in order to find the value of Rx. So Rx is defined as R3 into R1 upon R2 plus Rb Ry upon Ra plus Rb plus Ry multiplied by R1 by R2 minus Ra upon Rb. Now this particular expression is having last multiplier in the bracket, R1 upon R2 is equal to Ra upon Rb, which we have already defined to be equal. So these two parts cancel each other and making the second term of the same expression to be 0. So finally we are getting the value of Rx to be equal to R3 into R1 upon R2. So this is the final expression of the Kelvin's bridge. Please show the diagram in the book. The diagram in the book, please. Okay, here is shown a practical Kelvin's double bridge. The practical Kelvin's double bridge is used to measure the values of resistance starting from 10 ohm to as low as 10⁻⁻5 ohms. In order to reduce the effect of potential drop across the contacts, 9 standard resistors each of 0.001 ohm is connected in series along with a manganese bar of calibrated value 0.0011 ohm is connected with a sliding contact. Now in this particular diagram we can see that R1 and R2 are connected as a first two arms of the bridge, while the bar or connection of a bank of resistors each of 0.001 ohm is working as a switchable resistors along with a manganese bar that works for the calibration or tuning. Now these particular resistors are making sum of the total resistance as a branch R3. So this particular unit is working as a particular Kelvin's double bridge, and it can be utilized to measure a value of resistor that is as low as 0.00001 ohm, that is 10⁻⁻5 ohm. So these are the 2 points that we have discussed. First one is Wheatstone bridge, that is using 4 arms of the resistance measurement normally utilized to measure resistance above the value of 1 ohm, while the second one is Kelvin's double bridge normally utilized to measure the value of resistance for lower value starting from 10 ohms to as low as 10⁻⁻5 ohms. Switching over to the next topic of the same unit, that is AC bridges. The difference between DC bridge and AC bridge is well known, that is DC bridges are excited by DC potential or DC excitation, while AC bridges require AC excitation. So there is a term involved frequency along with phase. So this one thing is different. Along with that, the second thing is whatever is the detection of null, that is also to be AC. So instead of a simple galvanometer, we need to replace it with either a headphone or a higher sensitivity AC millivolt meter. Here the excitation source is normally audio frequency, or in specific cases it may be switched over to RF signals, while the detectors are simply galvanometer or high sensitivity measurement point. The balance conditions are also almost same, only thing is that resistance is replaced by reactance or impedance. That is, the condition is Z1 Z upon Z3, that is ratio of the impedance is equal to the second ratio of the impedance Z2 upon Z4. Now this particular condition is defining null condition where there is no AC signal passing from the intermediate detectors, and in this condition we can say that the bridge is balanced. Okay, the balance condition is rewritten here, that is Z1 Z4. In the part that something that is not visible is actually mentioning the phase angle θ1 and phase angle θ4 is equal to Z2 Z3 phase angle θ2 and phase angle θ3. So the same bridge expression is also containing two parts. One is magnitude part, that is simply represented as Z1 Z4 is equal to Z2 Z3, that is called magnitude balancing, while the second part is involving phase balancing, that is equalization of the phase due to the AC components involved, whether it is L or C. That is θ1 plus θ4 should be equal to θ2 plus θ3. So as a result, there has to be equal phase across the branches. AC bridges. In general, an AC bridge is connected like this. An example is given here. An AC bridge is given with a particular condition. Arm AB is having resistance 200 ohm in series with a resistance or inductance 15.9 millihenry. Arm BC is containing resistance in series with capacitance C to 0.265 microfarad. Arm CD is unknown, while arm DA is containing 450 ohms. The bridge is excited with 1 kHz frequency, and we have to find the impedance of the branch CD. A simple expression is given here, that is Z1, that is impedance of the first branch, R plus J omega L, that is 200 plus J into 100 ohms. second branch impedance R plus 1 upon j omega c, that is R minus 1 upon j omega c, equivalent to 300 minus j 600 ohms. Z3 third branch impedance 450 ohms, while the fourth branch is unknown. So the fourth branch can be calculated by simple expressions Z2 Z3 upon Z1, reducing it to j 150 ohms. Now this is indicating that the component is containing value of inductance. Now this result is indicating that Z4 is a pure inductance because it is not having a 100% real component, only imaginary component is there, means it is having all values inductive and there is no resistance or any other kind of DC quantity involved. 150 ohms is given at 101 kilohertz. So reducing it to XL is equal to 1 upon directly 2 pi FL, we can get the value of L, that is equal to XL upon 2 pi F, reducing it to 23.9 millihenries. Different type of AC bridges are possible, starting with the first one, that is capacitance comparison bridge. Two types of comparison bridges are there. First we will discuss capacitance comparison, followed by inductance comparison. The name is given comparison bridge because we are having equal and opposite kind of nature of the two arms, that is at the bottom side, while upper arms are R1 and R2 to be resistive one. So two arms R1 and R2 are resistive, while R3 is having variable resistor and capacitor, while arm R4 is containing unknown resistors. The impedances are also Z1 is equal to R1, Z2 is equal to R2, Z3 being capacitive unit R3 minus j omega upon C, and Z4 again capacitive unit Rx minus j omega Cx. So these are the impedances given. Balance conditions as it is, Z1 Zx is equal to Z2 Z3, reducing it to a final value. The third expression after reduction goes to the value R1 Rx minus j omega R1 upon omega Cx equal to R2 R3 minus j omega R2 upon omega C3. Now this particular expression is having two different quantities. It's basically a complex expression containing real part as well as imaginary part. The real part will give you the value of resistors, while the imaginary part will give you value of either capacitor or inductance. Being capacitance bridge, you can reduce or you can get the value of capacitance from the imaginary part. So reducing the real part expressions and imaginary part expressions in a different way, we can get Rx to be equal to R2 R3 upon R1 and Cx to be equal to C3 R1 upon R2. So in the same way, you can go for solution of unknown value of capacitance and resistance. Here Cx is defined as the capacitance of the particular unknown capacitor, and Rx is defined as the leakage resistance of the same unknown capacitor. The second type of bridge in AC category is inductance comparison bridge. The only difference between capacitance comparison bridge and inductance comparison bridge is that the lower two arms are replaced with upper two arms remains as it is, that is both of the arms resistive, while the lower two arm R3 branch or the third arm is having an inductance connected along with a variable resistor, while the fourth arm is having unknown inductance connected for the measurement. Here we are indicating the unknown inductance as summation or as a series circuit of Lx along with Rx, where Lx is pure inductance while Rx is the resistive part of the same inductance. You can say its internal resistance. Impedance is summarizing Z1 is equal to R1, Z2 is equal to R2, Z3 being inductance along with series resistance, that is R3 plus j omega L3, and Z4, that is the fourth arm impedance, unknown internal resistance Rx plus j omega Lx as a inductance. Same balance conditions, Z1 Zx is equal to Z2 Z3, reducing to R1 Rx plus j R1 omega Lx is equal to R2 R3 plus j R2 omega L3. So this is again containing the similar two parts, real part as well as imaginary part. From the real part we have to extract the value of resistance, which we are calling internal resistance or material wire resistance of the inductor, while from the imaginary part we have to extract the value of inductor, which is the inductance value. The real part and imaginary parts separated R1 Rx is equal to R2 R3, and the imaginary part R1 omega Lx is equal to R2 omega Lx. From these two expressions we can get the value of unknown resistance Rx internal resistance of the unknown unknown inductor Rx is equal to R2 R3 upon R1, and the inductance Lx is equal to L3 R2 upon R1. Now these two branches are called comparison branch because we are simply making a comparison of inductor to inductor, that is the lower two arms are of the same nature in both of the cases, while in capacitor comparison we are having the similar kind of comparison of capacitor to capacitor. These two kind of units or these two kind of bridges are used for very small or very lower measurements. Other two branches are there. The first one, the next one is Maxwell's bridge. Maxwell's bridge is normally used for inductance measurement for lower and moderate quality factor coils. Now here comes the terms of quality factor, we will discuss a few minutes later. Here two arms are there, that is arm R1 is containing arm R2 and R3 are containing only and only resistors, while arm R1 is containing resistor along with capacitor in parallel, while arm R4 is containing unknown inductance for the measurement. The impedances are also shown. The first one is, as it is containing R1 and C1 in parallel, we are going for the admittance instead of impedance, that is Y1 is equal to 1 upon R1 plus j omega C1. Z2, that is impedance of the branch 2 or arm 2 R2, impedance of the arm 3 R3, impedance of arm 4, that is equal to Rx plus j omega Lx. Putting these values in the same balance expression, Z1 Zx is equal to Z2 plus Z3, we can again make separation of real part as well as imaginary part. Rx plus j omega L on the left hand side becomes equal to R2 R3 multiplied by 1 upon R1 plus j omega C1. Making real part and imaginary part separated, Rx becomes equal to R2 plus R3 upon R1, while imaginary parts compared together makes Lx is equal to C1 R2 upon R3. Now this again will give you the values. Whatever is the value of inductance and its internal impedance, internal resistance, can lead you to the value of quality factor. The quality factor Q is defined as inductive impedance divided by resistive impedance of the same inductor, that is omega Lx upon Rx. Putting these values in the expression, we can get that the Q factor Q defined as omega C1 R1. The C1 and R1 are placed in the arm R1. So whenever we are balancing the bridge by making settlement of R1 and R3, we are getting the final values of R1 C1, and these R1 C1 values will directly give you the quality factor. Maxwell bridge basically is used for measurement of inductor, is having a fixed capacitor in the first arm. Now this fixed arm capacitance is having some disadvantage because it interferes in the resistance reactance balance. You cannot balance it beyond certain limit, and this can be improved by placing a variable capacitor instead of the fixed one. This bridge can measure an inductance up to 1000 Henry, so that is normally a practical limit. The extreme high quality factor balancing resistor R1 becomes impractically high. Going back in the circuit, if we are having very high very high Q factor, then the resistance R becomes 0 in the unknown arm or in the arm 4. Now this particular 0 resistance or near 0 impedance is to be balanced by R1, that is in parallel with C1. So this requires very high value of R1, and this becomes practically impossible because you cannot go beyond 10 mega ohms. So this practical limitation is there, and that poses a limitation of measurement in a very high quality factor coils. So if you want to go for measurement of very high quality factor inductance, then we have to replace this bridge with another one, and for that specifically a new bridge is used, that is Hayes bridge. Hayes bridge is specifically designed for measurement of very high Q coils. Here the first arm is having a little bit of alteration. Instead of connecting resistor and capacitance in parallel, the resistor and capacitors are connected in series, except that there is no change in rest of the bridge. R2 fixed, R3 is variable, while the fourth arm is containing your unknown inductance. The impedance is as listed. Z1, that is impedance of the first arm, is equal to resistance R1 minus j upon omega C1. Z2, that is arm of the impedance 2 impedance of arm 2 R2. Z3, impedance of arm 3 R3. Z4, impedance of arm 4 as a series resistance or a internal resistance plus inductance, inductive impedance Rx plus j omega Lx. Hayes bridge. Series resistors along with the capacitor in the arm 1 is helping to offer phase angle at low resistance and thus help to measure inductance of a high Q coil. Going back to the circuit, now here we have placed resistor R1 and C1 and series. So this is going to give you a phase difference. So if you are making or if you are interested in having very high Q coil, the phase difference should be very small required. So this makes requirement of R1 to be 0. R1 ને તમે 0 ની nearest value સુધી લઈ જઈ શકો છો. So smaller the value of R1, it is better to have a phase difference and this gives you exact balance of the phase. So this kind of utility or this kind of arrangement makes it possible to go for measurement of coil with very high Q factor. Hayes bridge is highly preferred for high Q coil measurements. Balance expression Z1 Zx is equal to Z2 Z3 as normal. The Z1 is defined as R1 minus 1 upon j omega C1. Z2 Zx is defined as Rx plus j omega Lx is equal to R2 and R3. Now this particular unit can be reduced further to the next level, that is R1 Rx plus Lx upon C1 minus j Rx upon omega C1 plus j omega Lx R1 is equal to R2 R3, again containing two parts or separating two parts of real and imaginary type. The real type is reducing to R1 Rx plus Lx upon C1 is equal to R2 R3 and imaginary part Rx upon omega C1 is equal to omega Lx upon omega Lx into R1. These two expressions can be reduced further to the values of Lx and Rx. Lx is defined as R2 R3 C1 upon 1 plus omega R1 C1 square and Rx is defined as omega square C1 square R1 R2 R3 upon 1 plus omega R1 C1 square. Here quality factor is omega R1 C1 as is defined previously in the Maxwell's bridge. We can replace omega R1 C1 in the expression for Lx, that is Lx is defined as R2 R3 C1 upon 1 plus 1 upon Q square, while Rx is defined as omega C1 R1 R2 R3 upon 1 plus Q square. So this is how we can convert the values of inductor and its internal resistance to the quality factor. The next type of bridge that is used for inductor, here is to be made correction, it is used for capacitance measurement instead of inductance measurement. Here the arms are also arranged in the same way as it is used in the first and second arm are as good as that of the Maxwell bridge. A series or a parallel combination of capacitor and resistor in the arm 1. R2 is variable instead of being fixed in the Maxwell bridge. Arm 3 is containing a fixed value of capacitor while arm 4 is having an unknown capacitor. Now here the unknown capacitance is represented as two parts or two units Cx and Rx, where Cx is the capacitive reactance and Rx is representing its leakage resistance. The admittance of the first arm, that is 1 upon R1 plus omega C1, the impedance of the arm 2 R2, impedance of arm 3 minus j upon omega C3, impedance of the arm 4, that is Rx minus j omega Cx. Putting these values in the balance expression, Z1 Zx is equal to Z2 Z3, Rx minus j omega Cx becomes equal R1 minus j omega Cx divided by 1 upon R1 j omega C1 is equal to minus j R2 omega C3. Reducing this expression, we can get finally Rx minus j omega Cx is equal to minus j R2 R1 omega C3 plus R2 C1 divided by C3. This particular expression we are separating the real part and imaginary part. Then Rx is equal to R2 C1 upon C3 and Cx is equal to R1 C3 upon R2. So thus we are having the values of unknown capacitance and its leakage resistance available here. Vein bridge. Vein bridge is basically utilized for measurement of frequency, and it has been invented or designed or invented for that, but can also be utilized to measure unknown capacitor. Here we are specifically showing the unknown frequency, how it is utilized for frequency. The arms 1 is containing R1 and C1 in series, arm 2 resistor, arm 3 is containing R3 and C3, while arm 4 is containing R4. So here we are not having any unknown value. Instead of that, we are having unknown frequency, and we are tuning the resistors R1 and R3 in order to make null condition. The impedance of the arms are represented as Z1 is equal to R1 minus j omega C1, Z2 is equal to R2. The admittance of the arm 3 Y3 is equal to 1 upon R3 plus j omega C3, and impedance of the arm 4 Z4 is equal to R4. Now this particular expression can be placed again in the same expression of balance condition, and this will yield you the values of frequency. So from the same expression we can get the values of frequency, because it is ultimately designed for that. If we are having, instead of unknown frequency, known frequency of excitation, we can place any of the arm to be unknown, and then in that case we will have that unknown value impedance to be measured. So this is what we have discussed, or what I have planned to discuss as either AC or DC bridges. The most important thing for the bridges is the measurement technique. The measurement technique of all the bridges is having a null detection. So this is basically a loadless kind of measurement. It does not extract any kind of voltage from the particular measurement. So this is having very high accuracy of measurement. So this is all about bridges. If anybody is having any questions, they are welcome. Thank you for viewing me.
SANDHAN, all Gujarat integrated classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.